Hello friends, here in this week we will talk about the aerosols, indoor aerosols, and for this particular lecture first we will cover aerosol basics. As we know, aerosols are an important pollutant when it comes to indoor air quality. So we will go a little bit into the aerosols, but mostly as it relates to the indoor environment. First we will have some basics. So, as a recap, aerosols are our small particles which are suspended in the atmosphere, and they are essentially a suspension of liquid, solid, or mixed particles with highly variable chemical composition and size distribution. And this variability is generally due to their different sources. So, you can have a cooking source, there can be a vehicular source which emits outdoor aerosols and they come inside. So the sources are different, so accordingly the aerosols will be different, and also the formation mechanisms. Maybe it says a soil particle that just resuspends or suspends from soil, or it could be uh, basically a gas that cools down and then condenses. So the formation mechanisms and sources can be different, and these lead to different characteristics of aerosols. So in this week we will basically cover indoor aerosols, a little bit basics, physicochemical properties, sources, and a little bit on health. So aerosols basically can come in a lot of irregular shapes and densities, and that basically again depends on their formation mechanisms and their sources. So they will be very irregular in shapes and densities. So then we have to somehow we have to make it normalized so that we can compare different aerosols from different sources, perhaps how they are behaving in terms of deposition. So we need to normalize them. So particle then can be defined in terms of their diameter, and we have three types: equivalent volume diameter, Stokes diameter, and the aerodynamic diameter. So first is the equivalent volume diameter. So here we have a aerosol of any irregular size, but with a volume V. Equivalent volume diameter is defined as the diameter of a sphere that would have the same volume and the same density as the actual particle. So the actual particle can have any shape of volume V. Our equivalent volume diameter will be the diameter of sphere with the same volume V. So here we have an irregular shape which with different width in different dimensions or different axes, and then we can standardize this to be a uniform sphere of the same density but with the same volume. So the radius of the sphere itself will be much different than the length dimension of the actual particle, but the total volume is same. So as we can see, this equivalent volume diameter is basically standardizing the shape with an equal spherical volume. Then so this is one. The next is our Stokes diameter. It's also sometimes termed as equivalent spherical diameter. This is the diameter of a sphere that would have the same settling velocity as the particle. So our irregular shaped particle is settling down. The Stokes diameter would be the diameter of the sphere which will have the same settling velocity. So basically this standardizes how they settle. So standardizes the settling velocity of the aerosol or the particle. Then finally we have the aerodynamic diameter, which is the particle of a standard density. So 1000 kg per meter cube that will settle in the air at the same velocity as the particle. So now we have a standard density and also the standard settling velocity in the air. So basically our aerodynamic diameter standardizes both the settling velocity and the particle density, and generally when we talk about PM 2.5, PM1, we are essentially talking about the aerodynamic diameter. Now what are the different types of aerosols? First is primary aerosols. These are basically primary, which means they are emitted directly from the sources. These sources, for example, combustion sources. So these are vehicles and different industries, different manufacturing plants or power plants, and we have our vehicles. So anything that leads to combustion of for example fossil fuels would be a primary aerosols. The other type of primary aerosols would be from mechanical processes, so like from operation of machinery. So we operate machinery and the aerosols are emitted. So these are basically immediately from the source. Then we have the secondary aerosols, which are not directly emitted, but they are produced from precursor gases. So precursor gases and the chemical reactions. Then they will generally form in terms of secondary aerosols. There will be a formation, or these will be forming substance of low volatilization. So when they have low volatility, they will condense into the solid or liquid phase, and these chemical reactions formations could be, for example, through different oxidation processes that may happen in the indoor environment. Okay, so now first we will look at primary aerosols. So primary aerosols mainly consist of two components, and we can naturally they would be either organic or inorganic. We can also have bioaerosols, which I guess for now we will put as organic, but we will have a section on bioaerosols later. So they will be organic and inorganic. So our primary aerosols are the inorganic primary aerosols are relatively large, often larger than 1 micrometer, and their origination is through like mineral dust, so maybe like soil suspension of soil. So when the soil is suspended, the smaller particles, smaller meaning more than 1 micrometer but less than maybe 10 micrometer, they will suspend in the air. Then we have sea spray, which is during wave action. So we can have these primary aerosols from sea spray and then from smoking also. So we have these inorganic primary aerosols which can originate from these kind of sources, and they are often larger than 1 micrometer in size. They are termed as coarse. We will look shortly at the definitions also. These coarser aerosols generally have short atmospheric lifetimes, and typically they may last only a few days in the atmosphere. So these primary inorganic aerosols will generally have shorter atmospheric lifetimes of a few days. So few days is enough for the aerosol emitted outdoor to come indoors, but they will not be remaining suspended for like weeks or months. Then we have the organic primary aerosols. These aerosols are also often known as carbonaceous aerosols, and these carbonaceous aerosols include organic carbon and the solid black carbon. So both kind of carbons would come under our organic aerosols, and the sources are essentially combustion processes, because fossil fuel burning would invariably lead to organic carbon and black carbon emissions. Biomass burning, which is also biomass, so biomass burning, and plant and microbial material. So anything that relates to like organic burning or organic sources, generally they will be these kind of sources. They are sources of carbonaceous aerosols. Now primary black carbon and organic carbon containing aerosols are generally smaller than 1. So our inorganic were generally more than 1 micrometer in diameter, but these primary black carbon and organic carbon are generally smaller than 1 micrometer in diameter. So black carbon is mainly an important anthropogenic light absorbing constituent of aerosols, and the main sources are as we would guess, they are combustion of fossil fuels, because basically fossil fuel is carbon. So varying degrees of burning of different types of fossil fuel burning, and maybe varying degree of their burning, they will be leading to different amounts of black carbon emissions to the atmosphere. And example of these fossil fuels are gasoline. So gasoline meaning like petrol, diesel, anything that leads is coming out from vehicular combustion. these would lead to emissions of black carbon aerosols. Then oil, so processes that include burning of oil will also lead to some amount of black carbon aerosols. Then we have coal. Coal again is a solid material, and when we burn coal, it will emit aerosols, and a constituent of these aerosols are black carbon aerosols. Then we have wood and other biomass. So these are again organic carbon based fuel, and when we burn these fuels, there are going to be again emissions of black carbon. Now we have secondary aerosols. These secondary aerosols are produced generally from precursors. So they are produced in the atmosphere from precursor gases by condensation of vapors on some pre-existing particles. So those pre-existing particles serve as a nucleus around which the gases will condense. So then of course the particle size will also increase, but this condensation will provide these particles will provide a nucleus around which these precursor gases can condense, and also by nucleation of new particles. So sometimes the nucleation of new particles itself is initiated maybe through gases or through different reactions, and we will have these secondary aerosol production. These are smaller than our coarse aerosols, and they are generally from few nanometers to 1 micrometer. So 1 micrometer is 1000 nanometers. So few nanometers to 1000 nanometers, or less than 1 micrometer. So these particles are quite small, and as a result they have a much larger or longer lifetime than the primary aerosols, which were more than 1 micrometer. If you recall, they were the lifetime of those aerosols in the atmosphere was about like few days, whereas these secondary aerosols have lifetimes of days to weeks. So that's a very substantial difference between our primary and secondary aerosols. These secondary aerosols again can consist of a mixture of compounds such as sulfates, nitrates, organic carbon and ammonium. So as we mentioned, they are formed by nucleation, which is these are molecules of low volatility, which means they will sort of condense. So these molecules will condense to form solid or liquid matter and the process of this formation can be through heterogeneous nucleation, which is a more common process. Heterogeneous nucleation means our newly formed substance is condensing on an existing small particle generally. So when there is a small particle, we have condensation happening, so these particles are also growing. And such kind of heterogeneous nucleation is quite effective on small and medium sized particles. The next form of nucleation is homogeneous nucleation, which means in the absence of pre-existing particles, these gases of low volatility will basically condense into one another, and then there will be a formation of secondary aerosols. So we have looked at primary, organic, inorganic and our secondary aerosols. The next thing to cover is aerosol sizes. So these aerosol sizes in nature can be of different degrees, ranging from sub-nanometer to several hundred micrometers. So we have our nanoparticles, which can generally be defined as less than 0.05 micrometer. So this is less than 50 nanometer. Then ultra fine, which is less than 0.1 micrometer. Then we have fine particles 0.1 to 2.5 micrometer. So 0.1 micrometer means 100 nanometers. So our fine range is 0.1 to 2.5, and then we have coarse. In this classification, the coarse particles are more than 2.5 micrometer. Now, what is then the next thing to consider is PM 2.5, which is the particulate matter which is passing a suitably designed sampling inlet with 50% efficiency cutoff at 2.5 micrometer aerodynamic diameter. That means through that specific inlet, 50% of particles which are 2.5 micrometer will pass, and that inlet is going to pass all the smaller particles. Similarly, PM10 would be for 10 micrometer aerodynamic diameter. PM10 would be the particles passing through an inlet for which particles of 10 micrometer, half of those particles will pass through. 50% of the total existing 10 micrometer particles will pass through that inlet, and the remaining not, and the particles of smaller size will pass through. So this is a PM 2.5, PM10. Now here we can sort of relate that in practical terms, and we will go larger to smaller. So these kind of things are visible with the human eye. Aeroplane length, so that's like 70 meters, quite high. A human is about 2 meters. This is 10 to the power 0, so 1 meter. Then we go millimeter. So a baseball or a tennis ball, approximately we are looking at 7.5 to 8 centimeters, so 75 millimeter. An ant is about 7 mm. Looking here, we have like a coin which is 20 mm, or a pinhead which is around 2 mm. Now we are going towards micrometers. So now we have beach sand. Beach sand is around 200 micrometers. A human hair size is around 70 micrometer. So now we are looking at PM10. So PM10 generally would be smaller than the human hair, more difficult to see with the human eye, and generally to better see them we need a light microscope. So maybe not very high power, but some light microscope. PM 2.5 we have around 2 to 2.5 micrometer, and in comparison the red blood cell is around 7 micrometer. So these things we can have through a light microscope. Now if we go lower than this, we are looking at nanometers, and now we can see these are viruses which are 70 mm, so rubella virus, 20 mm influenza virus. Cell membrane is 7 nanometers, so that's very thin. Our DNA strand would be around 2 nanometers. To look at these kind of scales, we cannot no longer rely on light microscopes, but we need a more powerful electron microscope. So now we kind of, in a way, we can sort of physically imagine how big or how small the particles are, and essentially generally we are talking about 0.1 micrometer, 2.5 micrometers. So we are at this stage, PM 2.5. 100 micrometer would be 0.1 micrometer, so just a little bit more than the rubella virus, which is 70 nanometer. So from this range to this range, we have important aerosol diameters we have just talked about. Physically, again we can see in this case we have a beach fine sand from the beach, 90 micrometer, then a human hair strand 50 to 70. In comparison, now we see PM10 which would be less than 10 micrometer. Now you see how much low it is, and then we have PM 2.5 which will be much lower, but these are sort of suspended in here. This is not completely to scale, but we can see in comparison how different they are. Now we can do some classification also. So on the x-axis we have the diameter in micrometers. So 0.001 micrometer, which is 1 nanometer. This is 0.01 micrometer, 0.1 micrometer, 1, 10, 100 micrometers. So less than 0.1 micrometer we are generally talking as ultra fine PM particulate matter, and this is like PM 0.1. So you see here less than 0.1. Less than 0.01 micrometer, so basically less than 10 nanometer, we have the nucleation mode particles. We will look at them in the next slides. These are generally condensed organic carbon or sulfuric acid vapors, and maybe they can also be in a clean environment. Then as we go a little bit more, we have Aitken mode, which is formed from particles which are emitted from like fresh high temperature emissions. and can contain like organic carbon, sulfuric acid and metal vapors. We are at condensation mode around 0.1. Then we have the accumulation particles, which are 0.1 to around 1 micrometer approximately. These are our sulfate, nitrate, ammonium, aerosols, organic carbon, elemental carbon, heavy metals and fine geological material. At 2.5 we are at this level, which can be including droplet mode. Then as we go more and more, we are here now into coarse mode, and these are our geological material, pollen, sea salt, dust based aerosols, as we looked a few minutes ago. So these are our coarse mode, and here we are also having total suspended particles and PM10. Nucleation modes are typically considered to be less than 0.05 micrometer, but sometimes this as 0.05 only and this as Aitken mode. These are generally our newly formed particles, so from different sources, including high temperature sources. The ultra fine nucleation mode will condense and become Aitken, and then they will condense and grow larger. These are relatively short lives, and they will relatively quickly transform to the larger particles. These aerosols quite efficiently will deposit to surface due to their high tendency for Brownian motion. So they will have Brownian motion, stick to the surface, and that is basically a deposition. After our nucleation mode, we will have accumulation modes. So after the growth of nucleation particles by condensation and coagulation, our accumulation mode particles will be formed, typically less than 1 micrometer and more than the nucleation mode sizes. So between, here we have written approximately between 0.05 to 1 or 0.05 or 0.1 to 1. These particles are too large to have rapid Brownian motion, so they will not have so much Brownian motion and deposit on the surface, but they are too small to settle by gravity also. So these, you can think of these particles as having the least amount of deposition and the most amount of residence time in the air. Further growth is inhibited after our nucleation, condensation. These particles come in accumulation mode, but the Brownian motion is not as rapid. So future growth is inhibited as coagulation is not as rapid as fine and coarse particles. So not as rapid as fine particles, and coarse particles anyways will deposit better. So there are barriers to growth of these particles by condensation. So these particles have longer atmospheric times, typically 7 to 30 days in the open atmosphere. Then we have the coarse particle mode. As we see, these are, these can be dust or wind-blown soil or sea sprays, pollens, or they can be mechanically generated, which means not by nucleation or condensation, typically more than 1 micrometer, and such particles have a better chance of settling by gravity. In this slide we have some PM sources. So here in the living room we have fireplace sometimes. So fireplace means wood burning. Wood burning is aerosols, coarser generally. Smoking is there. Then we have sort of a study room kind of place. We have accumulated dust which can be resuspended. Someone may also light an incense, so that will release aerosols. In kitchen, cooking will release aerosols. In bathroom and other rooms, one can have candles. Then we can have vacuum cleaners which can also act as PM sources. In this slide we are looking at the characteristics of aerosols from different sources. So here on the x-axis we have ultra fine particle concentrations in number per centimeter cube, in thousands of number per centimeter cube, and the scenarios are before burning in an indoor environment. So could be it's like a test room, Then when the activity has started during burning, then 5 minutes after burning, 10 minutes after, 15 minutes after, 30 minutes after. So in this way we see first tobacco cigarette. So before burning there is some background. During burning, so the background is less than 25, more like 10,000 per centimeter cube. Just during burning it goes up to 250, 270,000. So almost like a 30 times increase. Then after this activity is over, 5 minutes later the concentrations drop down sharply, and then a little bit more, but even 30 minutes after burning we are still looking at more than 2 times the concentrations in indoor air. But we see during burning there is a sharp increase. These are mosquito coils. Now in mosquito coils we have during burning some release, and then there is after 5 minutes after burning the concentration actually increase. So this could be probably due to nucleation, and then the concentrations decrease to again a higher value than our original background concentration, which was in black color. This is incense burning. Again we see the concentrations increase, something around mosquito coil as well. Here the concentrations again just during burning they are almost 6 times, 5 to 6 times the background original concentration. Then they slowly are decreasing 5 minutes after, 20, 30 minutes after. So it's almost maybe a little bit less than 2 or approximately 2 times the original concentration. This is e-cigarettes. Again e-cigarettes are also performing similar to incense during the activity. Then there is a slight increase after, again maybe due to formation, nucleation and accumulation of particles, and then they are decreasing. Cooking also same. So the concentration increases almost 6-7 times during the cooking, but there is even higher concentration 5 minutes after. So again this indicates the formation of secondary aerosols. After that the aerosols may deposit or accumulate, and then they grow in size and maybe there is a better removal. So the concentrations have decreased, but we see here that this yellow color, 30 minutes after cooking the concentrations are still quite high after the cooking activity compared to tobacco smoking or mosquito coil or incense or e-cigarettes or even candles. So cooking actually is leading to more lasting aerosols. Then we have candle. So candle, immediately during the burning the concentrations are almost 12 to 15 times, and they will rapidly decrease up till 30 minutes. These are ultra fine. Similar behavior is seen for PM1. In PM1 we will go from incense. So again the incense burning will increase the PM1 concentration by approximately more than 5 times. The concentrations are about similar after 5 minutes, and then they go down quite rapidly between 10 and 20 minutes after the burning. In mosquito coil, again as previously, we have certain numbers during the activity, during the coil burning. After 5 minutes they slightly increase in concentration, then go down. Same goes for candle. There is some increase, then more increase, then decrease. In tobacco smoking, the PM concentrations don't decrease that rapidly. They are essentially similar between these activity and 5 minutes later, and a little bit higher after 10 minutes. After 10 minutes, from 10 to 20, they decrease. In cooking, the decrease does not happen that much. So we see our during burning concentrations are again quite high. They increase even more after 5 minutes, and then 10 to 20 minutes they decrease from 5 minutes, but not so much among each other. So again, cooking, as we saw for the ultra fine, cooking is cooking produces aerosols that do not go down in concentrations as quickly as other sources. And here e-cigarettes, you see, during the activity and immediately 5 minutes after the activity, the concentrations are actually the highest. But then very rapidly they go down to almost like other activities such as incense or candle. And then after 20 minutes they go down more, but they are still higher than the background concentration. Here we have PM 2.5. Again, similar thing is observed in e-cigarettes. 0 and 5 minutes they are very high, go down. In cooking, again, so there is a different background. So cooking leads to high concentration, but it does not decrease immediately. They kind of stabilize for longer time. In tobacco cigarette, we are seeing something similar for 0 to 10 minutes, but then the concentration go down. Candle PM 2.5 emissions are much lower. Mosquito coil does release some PM 2.5, and then incense. Finally, we have PM 10. Again, same behavior in e-cigarettes, very rapid increase, then some decrease. There is very little change between 0 and 5, but then a very rapid decrease. In cooking, there is increase and then a little bit of more stabilization. See, again, they are similar, although the background is higher. The concentrations after the activity are not decreasing as fast, otherwise they would have gone quite down. Tobacco and candle, see here again, candle in PM 10 scenario, the candles also are not decreasing very rapidly. They are almost similar as similar concentrations between 5 minutes, 10 minutes, 20 minutes. Mosquito coil, there is slight decrease, but again much higher than the background. Incense is not releasing as much. Now, there are various factors that may influence the indoor particulate matter burden. One, of course, because we have seen outdoor air can be source of indoor air pollution. So, we have ambient concentrations, air exchange rates, then penetration factors, then sedimentation in the indoor environment, and also what are the resuspension mechanisms, like people walking will resuspend. So, sedimentation and resuspension mechanisms. Now, aerosols in the indoor atmosphere can originate from various sources. Also, as we saw, outdoor particles can infiltrate, and then they can also be formed as secondary aerosols through indoor gas to particle or gaseous phase reactions. So, we will see now some profiles of different sources. So, first we will look at PNSD, particle number size distribution. Vacuum cleaning, generally these particles will exist in the nucleation mode, less than 30 nanometer approximately. When we have indoor combustion aerosols, cooking, smoking, incense, they are quite more in the accumulation mode, 100 nanometer, which is 0.1 micrometer. And as we've seen in the previous figure, especially for cooking, we see that the concentrations are not going down as rapidly because the particles are more in accumulation mode. Then resuspension aerosols are more in the fine and coarse modes, but generally in this more than 1 micrometer sizes. Aerosols from cooking can naturally, because we are talking about carbon based materials, they will contain organic compounds and as well as soot. But most chemical components of vacuum cleaning, so these are more mechanical, they are crystalline solids. Now, so these are different sources and different profiles, but we know that even for similar sources, sometimes indoor aerosols can show different physical and chemical properties. So, now there is also been observed that the chemical composition of cooking aerosols has a wide variety of components, and it depends on many factors such as what food is being cooked, what oil is being used, what is the temperature of cooking, what is the cooking style, and also naturally the kitchen ventilation also. And all of these factors will lead to a particular PM characteristics in a cooking environment. So we will summarize the lecture now. We have sort of seen the basics about aerosol sizes, different types of modes, nucleation, Atkin accumulation, then coarse modes. Then different sources and the sizes. So we have seen some figures on incense, mosquito coils, tobacco smoking, e-cigarettes and cooking, and how they may, different types of sources actually lead to different types of particles in different modes. And especially in cooking, we saw that the particles concentration increased after as soon as the cooking activity was done, and they don't decrease as rapidly up to 20 to 30 minutes after the cooking, and largely because the particles are in accumulation mode, which have a poor deposition compared to poor deposition or removal mechanisms compared to the nucleation mode or the coarse mode. So this concludes this lecture. In the next lecture, we will look a little bit into the aerosol dynamics in the indoor environment.